want to find H max before slipping. Right, 0.8. We don't know anything about her height or the width of her foot. She's always standing on a single foot here. I'm going to model her foot where it contacts the slide. Since I don't know anything else, I'll model that as just a point of contact between her shoe and the slide. What are going to be the forces acting on her shoe where it contacts the slide? Yeah.
Would be a normal force perpendicular to the slide?
Right. So since I'm simplifying this down to a point of contact, I'm going to kind of zoom in on this. So the slide is going to have some axis. The normal force is always going to be perpendicular to that axis. I'll call that lowercase n. Right. So she's on 1 foot, so all of her weight will be down. Right. Friction between her foot and the slide, and this will be along the axis of the slide. We presume that she'll slide down, so the friction force will be up and to the right in this picture. Right, it's along a function. Previous ones, like the crates or the one we just looked at, the surfaces were horizontal their entire length. It didn't the angle of the normal force wouldn't change along it. Here, depending on how high she is on the slide or how far to the right she is, the axis of the slide is going to shift. So we want our free body diagram to be good for anywhere she is. So how can we make this a more general picture to determine what the angle or what direction FR is pointing and what direction N is pointing? We can take the derivative, which tells us the slope at any point x. We're told that y is 1/3 x squared. The slope is just the derivative of that, so 2/3 or 2x over 3 would be dy dx. Meaning, we can take this, we zoomed in and we're saying where it's in contact, we can make that into a straight line. This is going to have, and the friction force is along that. For any value of x, we know at least the ratio of the rise to the run. So we can say the rise is 2x to a run of 3, making this ratio triangle, this is one way we could do it, making the ratio triangle then 9 plus 4x squared, the square root of that. And now it'll tell us the direction of the friction force for any value of x that we go. Since the normal force is perpendicular to that axis, as we saw in the past, if we use the ratio triangle approach, all we have to do is flip what's the horizontal and what's the vertical. So for the normal force, the horizontal will be the 2x, the vertical will be the 3. And we can have a hypotenuse of square root of 9 plus 4x squared. Now the free body diagram is good for any value of x, because what's going to happen is she goes up this slide, the normal force is going to get more and more horizontal, the friction force should become more and more vertical. So it is a function of x here. In the x direction, we'll have a component of our friction force, the horizontal component, so 3 over root 9 plus 4x squared, minus 2x over 9 plus 4x squared times n. As long as the denominator is not 0, which it can't be for any positive or real value of x here, I can multiply through by the denominator and simplify this so it's a little bit easier to use. So equation 1 I can just write as 3fr minus 2x times n. The y direction has her weight down. plus the vertical component of the normal force plus the vertical component of the frictional force. I can't take a moment equation because there's no dimensions here. The sum of moments is not going to help me. But again, what am I looking for? How high can she climb before she starts to slide down the slide here? So what else is going to be true besides my equilibrium equations? Well, the normal force won't be equal to 0. That would be if she was like jumping off of the slide. But here we're worried about her starting to slip down the slide. Yeah.
Frictional force is at its maximum.
Right, so the friction between her shoes and the slide is at its maximum value, so she's on the verge of then starting to slide back down. So the friction force is mu, which is 0.8 times n, when she's on the verge of slipping. Using equation 3, I can put that into equation 1.1 and say that 0 is, so 3 times 0.8 n minus 2x times n. And actually, I'm assuming that my normal force is not 0, so I can divide through by n. In which case, when x is equal to 1.2, is when the friction force will be at its maximum value. What we're trying to find is how high she can climb before this is going to happen. So what's the last step that we have to go through to find what ultimately we were after? Right, we know the relationship between the horizontal distance. I put everything here in terms of x to analyze it. I could have actually done this with y. I think it was easier with x. If I know how far to the right she is, because of the way that this the slide is designed, I can put and find that her height will be 1.2 squared over 3. So the highest she can climb the slide before she starts to slide down without holding on and with only 1 foot is 0.48 meters above the ground.